Hi there! These are the same operations. In fact, doing this is equivalent to do 2 to the 2 times 2 to the 2, which is 2 to the 2 plus 2, which is 2 to the 4, which is 16. So the operation we did here, is exactly this. So doing this is equivalent to do this, and in general you can do it with any base. So if you choose base 3, you have 9 times 9 equals 81, which is equivalent again to this. We say that there is an isomorphism between the two operations and between the set of numbers n and the set of numbers 2 to the n, this set with the sum and this set with the multiplication. In general, you can do it with any base, and this set of number is a set of real numbers and sum, and this is the set of positive real numbers, because when you take a power, it's always positive. So there is a isomorphism between these two sets, R with the sum and positive R plus with the multiplication. So this is the symbol of isomorphism, and these two sets with the respective operation being isomorphic means that they are basically the same thing. The most fundamental structure is the same. Their algebraic structure is the same. So two things are isomorphic when in algebra they work the same if you do the same operations. So you can mirror the two operations. This operation can be mirrored with this operation by taking, for example, n equals 2 to the n, n equals e to the n, and any bijective function which preserves the structure, which means that if you do an operation inside this set R and you take the function of this operation, it's like doing first the bijection f of n and f of n prime, and then doing the operation in this other set. So basically the only difference here are the name of the elements. Here n, here 2 to the n or e to the n. The name change, but if you abstract from the name, you are left only with the fundamental structure, which is the real mathematical object. So these two sets can be considered the same in algebra. So what are algebraic structures? Well, they are of course sets, and they have some elements. They can be empty, but that's not very interesting if they are empty, and hopefully they have a structure, so they have an operation usually which describes the structure. So the structure between the elements is given by an operation. They can have various operations in general. The most simple structures, of course, will have only one operation, for example, groups. But now let's consider in general structures with a binary operation. A binary operation means that for every two elements you can define another element by doing this operation. So basically these other elements, let's say x, can be constructed by two other elements with the operation. It's related to these two elements with this operation. So basically a binary operation dot is represented like this, which means that you take an element from the set and another element from the set, you do the operation and you get another element on the set. So we consider set with closed binary operations. So basically the operation being closed means that the set is complete, because if we get an element outside the set, we could think to complete the set by including that element. These sets with a binary operation are called magmas, and they are very general because we only require a set and any binary operation. So it's interesting to study structures which have some restriction, and we will get to the restrictions. First, let's consider a general magma of two elements because a magma with one element, of course, you can only do this operation if the element is E and get E. That's the only possible structure, so there is only one magma or one element. And now let's consider a magma of two elements, like E and A. You can draw an operation diagram. So binary operation diagrams are drawn like this. You have here the two rows and two columns if you have two elements in the magma, E and A, and this, in this place you put the operation A times A, and usually we will write this like this. So we have the operation of A and B, we usually write it A times B, which is more convenient usually. And so here it can be an element of only of the set because it's closed. So we can have, for example, E, but we can also have another one with A instead of E. Now I'm drawing only this part because this is the same. And here, for example, A, here E, A, where in general you can put any element. Also they can all be E, or the operations can give E. So E is an element which absorbs all the other. Basically, they can all be A. They are very general for any combination, and the number of magmas like this is given by the tables you can draw up to renaming the elements, because of course if you exchange the column and the rows and then exchange E with A, you get the same magma, you just change the name of the elements. And think about magma with three elements. You have really a lot of possible number of magmas. So magmas are very general, and we should look for a structure, a kind of structure which is less general and maybe more interesting to study. So let's say we want to investigate the structure of a given magma. So we have an element 1 in magma, and let's say we discover that this is related to 2 and 3 by the binary operation. So this is generated by this operation. And then we discover that 2 is generated by the operation between 4 and 5, for example, and so on. So we are relating the elements more and more, and we are investigating the structure. We are discovering the structure of the magma. So we said that we can write this operation as 2 times 3, and this can be seen in a real set of objects. For example, you do the action 3 and then you do the action 2 to the element. And if we discover that 2 is the operation between 4 and 5, we can say that 2 is like doing 5 and then doing 4. So this is equivalent to doing 3 and then doing 5 and then doing 4. So we are giving an order, we are thinking about an order. But what's the trouble with this? Because we are relating something very abstract to something concrete, which is doing operation after operation. What's the trouble? That, for example, let's say we have this operation. Instead of this being grouped together, we have 5 and 3 grouped together. So you would write this with parentheses like 4 times 5 times 3, and this like 4 times 5 times 3. So if we have this kind of structure that these represent actions made one after another, then we are assuming the associative property, right? Because if these are actions, then doing 3 and then 5 and then 4 is exactly like doing 3 and then 5, 3 and then 5 and then 4. Because in the actions we are thinking of, only the order matter, but not how you group the actions together, right? But in general, this is not a property of any magma, because remember that if we don't have any restriction, we can generate elements, we can create magmas by putting always new elements with new operations. So we can call it 6, for example, and put it in our magma. And this becomes 6 times 3. And if we do this instead, we can call it 7. We can take an element which is not yet in our magma and create another magma, and this will become 4 and 7 in that magma. So these are chosen very arbitrarily. So these are not necessarily the same, because they can be arbitrarily chosen. So magmas don't necessarily correspond to this intuition of doing actions after actions and so on. So there is not an intrinsic order in the structure of the magmas. This kind of order, the order of actions, is equivalent to the associative property. So we can think to, if we are interested in associative properties, so in relating structures to actions, to real actions, we can think to assume the associative property and study those magmas which has the associative property. So our first restriction, the associative property. So now we can create a ternary operation, which is actually a binary operation of a binary operation. And since only the order matters, because these are the same, we can simplify the writing and write it like 1 times 2 times 3. And where you put the parentheses does not matter. So we ended up talking about actions, and let's move on trying to construct magmas which can represent certain types of actions. And let's see if we can restrict ourselves even more, so find other restrictions to represent certain types of interesting actions. So let's now consider our magma as a set of actions acting on some set X. So X is not our magma. Our magma is a set of operations on X, and we are using X just to find a particular kind of magma. But we are not interested in X in itself, but on the magma. The set X is needed for us as an intuition to find this magma. So our set can have elements, for example 1, 2, 3, it can be finite or infinite. And the simplest kind of actions on these elements are symmetries. Symmetries are operations which take you from a state X to a state X prime, which is equivalent to X, which means the structure of X will not change. So you basically only renamed the elements. So you can think of a symmetry as a renaming of the elements of X. So basically it's a permutation of the names. You can think of symmetries as permutations. So you exchange these two names and you get this, and this symmetry is equivalent, for example, to a reflection of this triangle through this line, because you exchange these points. If you do instead a cycle of the names, you have 1, 3, 2, you are doing a rotation, for example, of this triangle. So you can relate permutations to a lot of things intuitively, like rotations and reflections of polygons and so on. But fundamentally you are doing permutations. So every symmetry can be treated as a permutation of elements. It's easy to see that not all associative magmas can represent permutations. For example, you can have a magma with an element 4 which is not generated by other operations. And this means that in the table of operations, 4 does not appear inside. You can have a magma like this, but clearly every permutation can be generated by other permutations, because if you have the set 1, 2, 3, 4, and you have 1, 3, 2, 4, this can be generated first by doing a totally different permutation like this, and then doing another permutation like this. And you can do this with any permutation on any numbers. It should be pretty clear. But which property does this correspond to? Well, this is a more general property of a more specific property of permutations. Permutations are invertible functions. They are bijective functions. And is it clear? You can always undo permutations. So, if for any permutation A, there exists a permutation a to the minus 1, such that A times a to the minus 1 gives the identity, and the identity is the permutation which does nothing. So in our set, we must have an identity, and for each permutation, an inverse which takes us to that identity. What is a consequence of this property? Well, let's say that A times B is C, and to obtain C, you can also do A times D. So the column A, so the row A presents C 2 times. So you have A times B equals C, A times D equals C. If you can undo A, so you multiply the left side by A to the minus 1, and you use the associative property, so A times minus 1 times AB is A to the minus 1 times A times B, and this is the identity, which is the permutation which does nothing. So this is B, because you can write the identity property as identity times A equals A for any element A. Then multiplying both the sides by A to the minus 1, you have here B equals A to the minus 1C, and here D equals A to the minus 1C. So B and D must be equal. So these are the same column. So it is not possible to have the same element in the same column. This is basically the Sudoku property. So the identity inverse property, I call it the Sudoku property, because if you want to create the table, the operation table, you must make sure that in this column A appears only once, and also in this row, and so on. So here you can't have A, you will have B, and so on. So you will end up having all the elements in this column. So at the end, all the elements will be present. So, and also in the row. So if we have the identity inverse property with the associative property, all the elements are in the operation table. So this does exactly the property we were looking for. So what did we find? We found the subsets of permutations, closed subset of permutations with a binary operation given by the composition of functions or of permutations, being the permutations functions, and all the all the magmas which are isomorphic to these subsets of permutations with a composition of function as operation are called groups. So we found the groups. So groups are those magmas which have these properties: the associative property, the identity property, which means that there exists an element which is usually written E, such that if you do the operation with A, it does nothing, and the inverse property, so there is, for every element A, there is an element A to the minus 1, such that the operation between the two, and you can do it both ways, of course, gives E. And also notice that with the concept of isomorphism, we completely abstracted from the set on which we did the operations, and we are now considering only the operations themselves and the properties of the set of operations. Now you can have some doubts. For example, is there only one identity element? Can I have two elements that do nothing? For example, E times A equals A, and also D times A equal A for any element A of the group? Well, we can check that, because we can easily see that if we, as A we take D, we have E times D equals E. But if we consider E as the identity element, we also have that this is D. So, since these are equal, so all the identities are equal. So there is only one identity indeed. And also, is there only one inverse? So if A times B equals E, is there any other element D such that A times D equals E? Well, this is one case of the property we have seen before, for which you can't have the same element twice in the operation table in one row, so in the same row. So if you have A times B equals E and A times D equals E, they must be the same column, so B must be equals to D. You can also see with these operations which we did before. So inverses are also unique. Now going back to the properties of our operation, we have that associativity implies that only order matters between elements, so we can create an operation with a string, with an ordered string, A, B, C, D, and so on. And there is another property which is not required, but it's another property which can be used to categorize some groups, which is commutativity. Some groups are commutative, which means AB equals BA, so you can exchange the elements between them, and if you apply this with associativity, you have that only the elements matter and not the order. So also the order does not matter with commutativity. So you have this an ordered set of elements. However you arrange the elements in a string, you will end up with the same operation. Now, commutative groups are called abelian groups. So abelian groups are commutative groups. That will be a useful terminology to categorize groups. So if you have a set A with an operation dot, to check if it is a group, you have to check that it is closed under this operation, which means basically that you already have the whole set, so A is complete. And this is often called the axiom 0, the closure, axiom 0, because it is already in the definition of binary operation, the closure. It's not an axiom of the group itself. If you consider already that a property of magmas, then you have to check associativity, and then you have to check if there is an identity element, and then if there is also an inverse element for every element of the group. Now we will see some examples, and we will also calculate the order, which is the number of the elements of the group, can be finite or infinite, and if it is an abelian group. Now let's consider, for example, the set of integer numbers that with the summation plus. The summation is associative, the identity is 0, the inverse for any element n is minus n, because n minus n, n plus minus n is 0, the identity. It's also abelian because sum is also commutative, and the order is infinite because it has infinite elements. Now it is closed because we already have all the integer numbers. the summation of two integer numbers is an integer number, so we already have all the elements in the set. So we already have the set with all the elements. If we had, for example, -2, -1, 0, 1, 2, instead of that, that would not be closed because -2 plus -1 is -3, which is not inside this set. So this is not closed. But if instead of that we had, for example, only the multiples of 3z, the set of the multiples of 3, so 0, -3, 3, -6, 6, -9, 9, and so on, it is easy to see that this is closed because you take any two elements, 3a and 3b. If you do the operation, if you sum them together, you end up with 3 times a plus b, which is also a multiple of 3. So we already have all the elements generated by the sum inside our set. So it's complete. So it is closed under this operation. So also 3z with the sum is a group. Now when a subset of A is also a group with the same operation, we call it a subgroup of A. So 3z is a subgroup of Z, and of course any subset nz, so the sets multiples of n for every n are subgroups of Z, are subsets of Z, and they are also groups with the operation plus, because they have the identity element 0, they have for every element an a, the inverse minus an a is inside the set, the operation is the same, so it has also here the associative property. It is closed, so it is a subgroup of Z. The order is infinite, apart for the case where n is 0. In that case, it is only the set 0, the group of order 1, and it is also always abelian. R and Z, the only subgroups of Z, it is easy to check that this is the case, because look for the smallest element in your subgroup A. Let's say it is 2. If it is 2, then you do -2 and you get 4. Also the inverse of -2, 2 is in the group, so 2 plus 2 is 4, and so on. You already generate all the multiples of 2. If you start by 3, you generate with the sum all the multiples of 3, and so on. In general, if you start by the smallest element n, you can generate the group with already all the multiples of n, so you will always end up with nz. So all the subgroups of Z with sum are nz. You can also check that the set of rational numbers with sum is also a group. The identity element is always the same, 0, the inverse of A is minus A, the operation is associative, and it is also abelian because the operation is commutative, and the order is also infinite. We can check the set of integers modulus n. If you don't know what that means, it means it's very simple. The set of integers modulus n is the set of integers from 0 to n minus 1 with the operation plus n, which is the sum modulus n. And if you don't know what that means, now I will explain it very quickly. So 1 plus 4 is 5, and 1 plus 4 modulus 3 is 5 modulus 3, but numbers modulus 3 only goes from 0 to 2, so when they arrive to 3 they repeat, so actually modulus 3 they are 0, 1, 2, 0, 1, 2, so the result is 2, so 5 modulus 3 is 2. Basically, the numbers modulus n repeat at each cycle of n elements. So if you want to see what is A modulus n, you group the numbers in cycles of n, so until you get to your numbers A will be something greater than a multiple of n, and it will be a multiple of n plus d, and if d is less than n, then A is d modulus n. If d is greater than n, then you can still make another cycle of n, and so on until you get a d smaller than n. It is closed because summation repeats, and also summation is associative. The identity is 0, is always in the set, and it also has the inverse because, for example, you can also go to 0 with -1, for example, in this case would be 2, because 1 plus 2 here is 0 modulus 3, and so on. It is easy to check that this always corresponds to an element in the set. If you don't get to 0 with the number b, then you take b plus 1, and so on until you get to 0. The order is n, so they are finite groups, and they are also abelian because also in this case, of course, the summation is commutative. Now, is a set of real numbers with multiplication a group? It is closed. It is associative. The identity is 1, and the inverse is 1 divided by a for every a in the real numbers, except when a equals 0. A equals 0 does not have an inverse, so this is not a group. But if you remove the 0 and you get a star means the set of real numbers without 0, you get a group because you still have inverse for each number. The identity is 1, it is associative, it is closed because no operation between a and b different from 0 will give 0. It is also an abelian group, and the order is infinite. It's easy to check that as a group of this is, for example, the set of rational numbers without 0, because the multiplication between two rational numbers gives another rational number. So it is closed, and also the inverse of the rational number is a rational number. 1 is a rational number, the identity. It has infinite order, and it is also abelian. Another subgroup of a star with multiplication which is also a subgroup of Q star with multiplication is -1, 1. So the set only with -1 and 1, because -1 times 1, you can check the multiplication table because it has only 2 elements, so it's very easy. 1 minus 1, 1 minus 1. 1 times 1 is 1. 1 times -1 is -1. -1 times 1 is -1. -1 times -1 is 1. So it is closed because it always gives 1 and -1. It is associative, of course, and the identity is 1, as you can see. And the inverse, it is also abelian, and the order is 2. Now, before continuing, we answer these 2 doubts you can have. The inverse has a symmetric property, so the inverse of a to the -1 is a. In fact, this is the definition of the inverse, and you can read it either way. So if a to the -1 is the inverse of a, you can read it as a is the inverse of a to the -1. Now, the other doubt is, what is the inverse of the application of 2 operations? So what is the inverse of AB? AB means you first apply B, and then you apply A. So to undo this, you must first undo A, and then undo B. So the inverse is B to the -1, A to the -1. where the order of A and B is reversed. You can check this because by associative property you can group these two terms b to the minus 1. I write it here again. You can group these two, so this gives a to the minus 1, which gives E the identity. So b to the minus 1, a to the minus 1 is indeed the inverse of AB. Now let's look for finite groups. First, of order 1, so with only one element. There is obviously only one group of order 1, which is the group with only the identity element, which is the inverse of itself, and this is of course closed under any binary operation of which this is the identity. Then of order 2, we have various ways of finding groups, for example by multiplication tables. Of order 2, we see that if we name the elements 1 and 2, we must have one identity. Let's say it is 1, the identity. So here we have 1, 2, and here 1, 2. Then here we must have 1 by the Sudoku property. So we have only one group, one possible group of order 2. And obviously because it is the group with the identity and an element which is not the identity, but by closure A squared is the identity and A is the inverse of itself. And by order of an element A, I mean the least number n for which A to the n is the identity. So you repeat the operation A squared. If it is not the identity, you go on A cubed and so on until you arrive to A to the n equals E. Then A has order n. Now let's find the groups of order 3. Writing the multiplication table, if 1 is the identity, we have 1, 2, 3, 1, 2, 3. Then by the Sudoku property, here we can't have 3, so 3 must be here in this row. So here we have 1. Then here we must have 1, and here 2. So there is only one possible group of order 3. Instead of using the table, you can find it like this. It must have an identity E, another element, and another element A squared, and A to the cube equals E. Now, by using this method, why can't A squared be E? Because assuming A squared equals E, then we must have another element B in the set, and by closure, we must have that A times B is either A or E. If it is E, then A, the inverse of A, is B. But since A squared equals E, the inverse of A is A, not B, and we are assuming they are different elements. Otherwise we would have the group of order 2, which we have already seen. Instead, if A times B is A, then B is the identity element, but we are assuming that B is another element, and identities are unique. Same thing here, if AB equals B, then A is the identity element, which is not. So the set can't be closed. For it to be closed, we need A squared different from E, and A to the cube equals E. Now let's look for the groups of order 4. In the operation table, we choose 1 to be the identity element, 1, 2, 3, 4, 1, 2, 3, 4. Then, here we have two possibilities, it seems. We can't have 2, but we can have 1, 3, or 4. Of course, choosing between 3 or 4 is simply a renaming of the elements 3 and 4. So we have actually only two possibilities. One is having 1, and the other is having 3 or 4, and we choose 3. Let's say 3. Now I'm not drawing this external part because it's always the same for all the tables. So I'm drawing only the internal square. Now here we can't have 3, so we have 4, and here we have 3. Here we can't have 3, we can't have 1, we can't have 2, we must have 4. Here we must have O1, O2. So we have other two possibilities here. So we copy this 1, 2, 3, 4, 2, 3, 4. Now we can have 1, 0, 2. Let's say we have 1, so we are keeping 1 in the diagonal. And here let's say we have 2. If here we have 1, here we have 2. Here we have 3. Here we have 2, and here we have 1. And we have one group of order 4. Here instead we have 1, 2, 1, 3. Another group of order 4. Now we complete this table, and we have here 1, because we can't have 4 here. So here we have 4. Here we can't have 3, 2, or 4, so we must have 1. So here we have 4. Here we have either 2 or 1. We must have 2 here and 1 here. Here we must have 2, and here we must have 3. Now clearly these two groups are different, and these two groups are different because here every element has order 2, because multiplied by itself gives the identity, because we have 1 in the diagonal. Here instead we have only one element of order 2. But are these two different? We can check. We can exchange the names of 2 and 3, because names are arbitrary, so renaming doesn't change the structure of the group, and we get, by exchanging 2 with 3, this table. Then we can exchange 2 columns, because order of the elements is also arbitrary. Now order, not the exponent. By order I mean the way we put it in order in the tables. So exchanging columns and rows does not change the structure of the group. And now we want to exchange the 2 central columns and the 2 central rows, so that we can check the similarity with this table. So first we exchange the 2 central columns and we get this. Then we exchange the 2 central rows and we get this. And this is identical to this. So these two are the same group. So we have only 2 groups of order 4. So we can write this group like this. This is the group where all the elements have order 1. So we have the identity, which is 1. We have another element, a, which is, let's say, 2, and a squared is 1. So the orders here are 1 is the order of the identity, 2 is the order of a, another element of order 2, which is b, let's say 3, and b squared equals e. So here we must have, by closure, a times b, and a times b squared equals e. This can be verified also because it is symmetric with respect to the diagonal, so it is abelian. So ab times ab, we can exchange b and a, and we have a squared b squared equals e times a equals e. And this is the element 4. And of course we can exchange the labeling, because these elements are all equivalent. They are all elements of order 2. We can choose, for example, this to be 3, this to be 4, and a times b to be 2. This only changes the name. Now let's write this group. We have the identity 1, an element of order 2, which is 2, and now we can't choose 3 or 4 for the element of order 2, because only 2 has order 2. So orders, here we have order 1, order 2, and another element B, let's say 3. What's the order of 3? 3 times 3, 2. 2 times 3, 4. 4 times 3, 1. So it has order 4. And the other element, which corresponds to 4, what's its order? 4 times 4, 2. 2 times 2 times 4, 3. 3 times 4, 3 times 4, 1. So it has order 4. Now this element, which combination of A and B is? B squared is A, so it can't be B squared, it can be A squared because it's the identity element E, so it would be B cubed. In fact, 3 times 3 is 2, 2 times 3 is 4. By replacing A with B squared, we notice that our group is a set of the elements, is a set of the powers of B with b to the 4 equals E. When a group can be written as a set of power of only one element, we say that the element is a generator of the group. Now here either B or B cubed are generator of the groups because they both have order 4 and they are equivalent. But B squared is not a generator because repeated operation of B squared gives E B squared, and it only gives the subgroup E B squared, but not the whole group. The groups that have only one generator, so which contains only the power of one element, are called cyclic groups. So this is the cyclic group of order 4. And the three groups we found previously, the group of order 1, the group of order 2, and the group of order 3, are also cyclic groups. In general, the cyclic group of order n is the group which contains all the powers of one generator up to n minus 1, and C to the n, the generator to the nth power, is E. So this is why it is called cyclic, because by repeated application of the generator C, you get C squared, C to the third, and so on, C to the n minus 1, and then you go back to E. We use this notation for cyclic groups. We say that they are generated by an element notated as C, and C to the n is the identity. Groups in general can be described by their generators. For example, we write for a group generated by two elements, A and B, as AB, such that A to the m is E and B to the n is E, so A is of order, say, m, and B is of order n. And we have a relation between A and B, which we can always write as some combination of A and B equals to the identity. And this relation states how the two elements are interconnected. This is, for example, generated by two elements A and B of order 2, and this is the relation between A and B, which is equivalent to say that AB equals BA, so that the group is abelian. Now, looking for groups of high order with the operation table can take a very long time, and usually it is preferred to look for groups by studying the way to interconnect the generators of different orders. So this group notation is usually preferred to this group notation, and it also allows to better see the structure of the group. So now we can do something different. Instead of categorizing groups by the order, we can first categorizing them by the generators and the relations between the generators, and then categorize them by the order. Now we said, with one generator we have cyclic groups. The order of C is n. The order of C squared, n is even, you apply C squared and you can skip half of the pieces and you will arrive at the identity after n half steps. But if n is odd, then this is n minus 1, and by applying c squared you don't arrive in 0, but you arrive here, and from here you arrive here. So you missed the 0, and you have to do the cycle another time to arrive to 0. So you have to do n steps in total. So if n is odd, the order of c squared is n. And what is the order of c to the cube? It's perfectly analog to this. If you can divide n by 3, then you will end up in 0 after n divided by 3 steps. Otherwise, you will have to do n steps. In general, if n divides n, then c to the n has order n divided by m. If n is coprime with n, so they don't have factors in common, then the order of Cn will be n. In general, the order of c to the n is n divided the highest common factor between n and n. For example, in C10, the order of C4 is where you do c to the 4, c to the 8, then you get c to the second, then c to the 6, and then c to the 10, which is e. So the order of C4 is 1, 2, 3, 4, 5, is 5, which is 10 divided by 2, and 2 is the highest common factor between 10 and 4. And this is obviously because if m and n have a factor d in common, so we can write m equals dm prime and n equals dn prime, then n divided by d is an integer because it's n prime. So it can be an exponent, so we can exponentiate c to the n to n divided by d, and by writing n equals d times n prime, d and d cancel out, and we have c to the n prime times n, which we can invert the n prime with n, and we have c to the n c to the n to the n prime, which is e to the n prime, which is e, the identity. And the order is the minimum number for which c to the n elevated by n divided by d is the identity. And this minimum number is, of course, when d is the highest possible, so when d is the highest possible common factor between n and n. So when d is HCF, so highest common factor of n and n. So the subgroups of the cyclic groups are those subgroups generated by c to the n with order n divided by the highest common factor of between m and n, because obviously, as we have seen, this is the least possible numbers for which c to the n elevated to this is the identity. And these are all isomorphic, as you see, to the cyclic group of order n divided by the highest common factor between m and n. In particular, the cyclic group of infinite order is isomorphic to the integer numbers with summation, and it is generated by the element plus 1, with all its positive and negative powers. And also we have seen before that the subgroups of Z are exactly and Z, so they are E, for which n equals 0, and E is the identity, which is 0, and Z, where n is different from 0, in which case they are infinite, in which case they have infinite order. So when n is different from 0, actually they're all isomorphic between themselves and they are all isomorphic to Z. So we can say that Z has only two groups up to isomorphism. The trivial subgroup 0 and Z itself, because all the nz with n different from 0 are equivalent to Z. Now we come to an example of groups with two generators, dihedral groups. Dihedral groups represent the symmetries of polygons, so rotations and reflections. For example, this is an hexagon and this is a rotation. Rotation only rotates the vertices and it does not change the order of the vertices. And of course, for angles we have n rotations. So for example, 6 rotations for hexagons, since the identity is considered as a rotation of 0 degrees, so it counts as a rotation. And then we have reflections. For example, this is the reflection through this line which fixes 1 and 4 and switches 2 with 6 and 3 with 5. This is a reflection along this line which does not connect to vertices but to lines, and it does not fix any point. It switches 1 with 6, 2 with 5 and 3 with 4. So if n is odd, the reflections are vertex line. So we have n possible reflections. For example, in a pentagon we have this possible line of the reflection, this, and this. If n is even, we have n divided by 2 reflections, vertex. For example, and these reflections fix 2 points, while instead here they fixed only 1 point. For example, this is a possible line of reflection, 1, 2, 3, so 3 lines of reflections, point for the hexagon. And we have n divided by 2 reflections, line. So for example, this line of reflection, this, and this. So the total of reflections, n divided by 2 plus n divided by 2 equals n reflections, also when n is even. So it does not matter if n is even or odd, we will always have n rotations and n reflections. So reflections, point line or vertex line, fix 1 point. Reflections, point or vertex, fix 2 points. Reflections, line, fix 0 points. So what's so special about rotations and reflections? We know that rotations are quite special because they don't change the order of the vertices and they don't even change the reciprocal distances between the vertices. Do reflections, by the way, change the distances between the vertices? Well, in these two examples, we see that here we have the order 1, 2, 3, 4, 5, 6, and here we also have 1, 2, 3, 4, 5, 6, but with reversed order in the opposite direction. Here also we have 1, 2, 3, 4, 5, 6 in the opposite direction. So it looks like reflections only invert the direction, but they also don't change the reciprocal distances between the vertices. In fact, its reflection through one line is equivalent to a rotation in the third dimension along that line. So if we want to rotate along this axis, you can take a piece of paper with a transparent piece of paper with the hexagon and rotate it, and it's obvious that after the rotation the reciprocal distances haven't changed, but the order of the vertices has only been reversed, and you end up only with a composition of reversion of order and rotation. And I don't have a transparent piece of paper, so I'm using this. I have written the numbers 1, 2, 3, 4, 5 in order, so this represents a pentagon of vertices 1, 2, 3, 4, 5 in this order, and say that you want to do a reflection between the line passing by the vertex 2 and the line 3, 4, then you can rotate this like this, and you end up only with an inversion of order. As you can see, 1, 2, 3, 4, 5. Now it's in the opposite direction. So we can say that rotations and reflections are those permutations which, given a total order, they don't change the order, but they can only reverse the order. Those are the dihedral group associated to the n-gon, so a polygon with n sides, has 2 n elements. So the dihedral groups are notated like this, d2n, for the n-gon. So here, in the subscript, you don't have the number of sides of the n-gon, but the number of elements of the group, 2n. So for the triangle, it's not d3 but d6, because it has 3 rotations and 3 reflections. For the square, it's d8, for the pentagon, d10, and so on. So despite having n reflections, there is only one reflection state, we can say. We have the non-reflective state and the reflective state. The reflective state is all the states where the order has been reversed. And to generate any other reflection, it's enough to apply one reflection and then rotating after having applied the reflection. So we have 2 generators. One rotation, which is the rotation of the minimum angle, or any rotation which allows you to reach all the other rotations, so any r to the m, such that the greatest common factor between n and m is 1, because of course the subgroup of rotation is isomorphic to Cn, and we have seen that all the powers r to the m, with greatest common factor between m and n equals 1, generate the group. So we have r to the n equals E, and the other generator is reflections, any reflection, and the group of reflections is isomorphic to C2 because it has only 2 elements, the reflection and undoing the reflection. So S squared equals E, because any reflection, if you apply the reflection again, you come back to the original state. Now we have to write the relation between rotations and reflections, where we have said that you can reach one rotation by applying, you can reach any reflection by applying one reflection and then a number of rotations. In fact, the dihedral group, these up to the n minus 1, here you have the reflections S1, S2, S3, but any Si can be written as S times r to the power of a certain number m. And in particular, since reflections embed the order, if you rotate m times after having applied the reflection and then you reflect back, it's as if you have rotated backwards m times. So if you do reflection and then r to the m and then you reflect back, it's as if you had done r to the minus n. So this is our relation we must put here, but this is equivalent, this can be written as Rs equals r to the minus 1, because by repeated application of this, an associative property, we get this. So these two are equivalent. So this is the dihedral group, which can be written like this: r squared s, rs, r squared s, and so on. And is obviously closed because by combining any 2 elements of this by this relation, you end up with an element of this. For example, these are the rotations and reflections of the equilateral triangle. This is E, this is a rotation of 120 degrees, which is R, this is R squared, this is S, the reflection along this line, this is RS, and this is R squared S. And in particular, the dihedral group of order 6 is isomorphic to S3, the set of all the permutations on these 3 points. In fact, we can reach all the possible permutations with D6. But this is instead the group D8, the rotations and reflections of a square. And of course, this is not isomorphic to S8 because, S4, because S4 has 4 factorial elements. Of course, it's all the possible permutations of 4 elements, which is 24. Instead, here we have only 8 elements. Also, notice that D2n is obviously not abelian because R to the ms is different from R to the m, because of our relation. This is R to the minus ms, which is clearly different from this, unless R to the m is R to the minus m. So unless R to the m has order 2. So unless m is n divided by 2. Also, it's easy to verify what is obvious, that reflections have order 2, because given as a numeric reflection R to the ms, if we do it again, where R to the ms is S R to the minus n, so associative property, this is E, and we have R to the m, R to the minus n, which is E. Another way to generate groups is by considering 2 different groups and consider their operations independently. So you operate on an element like this, which has here the elements from this group, and here the elements from this group. Then the operation with another element, and same thing, this is in this group and this is in this group. The composition of the 2 operations, here the times and here the plus, the respective operations. So you are doing operations independently, and of course this forms a group because this is closed and the inverse is c to the minus 1, h to the minus 1, and the identity is E of G and E of H. So this group is called direct product of groups because the set is of course the Cartesian product G times H, and the operation is this operation, which we have defined like this. In particular, 2 subgroups of this group are always the sets G, E, where you have the identity here, and here any element from this group, which is isomorphic of course to G. So you basically are doing operations only on G, and you are ignoring the H, and also e.g. H isomorphic to H. And we can generalize it to a product of more groups, G1 times G2 times G3, and so on, also infinite groups. And this notation is obviously incorrect if you were having doubts. So this is the right notation. An example is a direct product between 2 cyclic groups, Cm and Cn, and if we take the generator Cn, its order is of course the lowest common multiple between n and m, because you have to wait that they reach simultaneously the identity because if this reaches the identity first, this maybe is still doing his cycle, then this repeats and so on, and when you elevate this to the lowest common multiple, they will reach simultaneously their identity elements. If the lowest common multiple is n times n, which is equivalent to the greatest common factor is 1, so m and n have no factor in common, this is isomorphic to Cmn. So an example is C2 times C3. If you start from here and you from C2, C3, so the pair with the two generators, and you multiply it by itself with the identity in 2, here C3 squared is not the identity yet, then it reaches the identity here, but here it is C2, and so on, and you must do it 6 times to get simultaneously the identity. In fact, the lowest common multiple between 2 and 3 is 2 times 3, which is 6. And of course, this is isomorphic to C6. In fact, it is a cyclic group of order 6 with this generator. Let's see another example of direct product. This is a direct product between the two cyclic groups of order 2, and these are the elements, and this is a product between these two, and they have all order 2. We can write them like this, and this is the set generated by A and B with A squared equals B squared equals AB squared equals E, and if you remember, this is the one of the two groups of order 4 we had found before. One was the cyclic group of order 4 and the other one was this. Of course, this can't be the cyclic group of order 4 because 2 and 2 are not co-primes. The highest common factor is 2, it's not 1. Now let's go back to study isomorphism. We said that the isomorphisms conserve the group structure and they also are bijective, which means for every element of this there corresponds exactly one element of this, so that the two groups are completely equivalent. Being it bijective, it means that it is invertible, so you can do the homomorphism either way, here with f from here to here and from here to here with f to the minus 1. Now we can also take this property separately from the bijectivity and study a certain type of function which is not invertible but which still processes the structure of operations. This in general is called homomorphism, and isomorphisms are bijective homomorphisms, but homomorphisms in general are not necessarily bijective. So homomorphisms comprehend all the types of transformations which preserve the structure one way but not the other way, which means some information is lost when going from here to here. So preserving the operation structure one way does not imply it preserving also the other way, so it does not imply bijection. An example is the homomorphism, which sends every element to the identity. In a homomorphism you can do operations in this and parallel, and this is like doing operations on this, right? So you can do A times B equals C, or also F of A times F of B equals F of C. If everything goes to the identity element, then this operation can be done here as D1 times D2 equals D3. Here instead it becomes E times E equals E, which is a trivial operation, and this is clearly a homomorphism, but it's definitely not bijective, because here you can still, when you do operations here, you can still distinguish between the elements on which you are operating. Here instead you can't distinguish between these two elements. If you did instead G4 times G5 equals G6, this is still E times E equals E, and you can't distinguish how you came to E. If you have to come back, you don't have a unique way to go back. You can associate it to any element here. So you can think of a homomorphism as sending not element to element but sets to sets. This is G, which is the union of these sets. These are sets and not elements, K, G1, G2. These instead are elements, E, H1, H2. And for example, K is a set of elements which are sent to E, G1 is a set which are sent to H1, G2 is a set which are sent to H2, and so on. So when you go from here to here, some information is lost. For example, if you do operations in G1, so G1 times G2, which belongs both to G1. If you do here, you are distinguishing between G1 and G2, but here you are not distinguishing between G1 and G2 because they both are H. So if also G3 belongs to G1, here you can't distinguish whether you are doing operations G1 times G2 and G1 times G3 and so on. So when going here, some information is lost. Let's first consider the set of elements which is sent to the identity. This is called the kernel. The kernel is the set of elements in G such that they are sent to the identity. This is the set we have seen in the example before. When you do operations in the kernel, K1, K2 equals K3, you have E times E equals E, but before we only had the set, the kernel, we only had the kernel because we were considering the homomorphism which sends everything to the identity. This homomorphism does not send everything to the identity, so this could be in general any other element here, but think about this. If this element is not in the kernel, it's one element from here, then this is not E because f of G1 equals E implies that G1 is in the kernel. So f of G1 is different from the identity, so this is different from the identity. But the identity turns the identity. In any group, it gives the identity. So this does not maintain a group structure, so it is not a homomorphism. So in every homomorphism, when we do operations on the kernel, we still get an element in the kernel. So the kernel is a subgroup of G. Now consider an element G1 which is not in the kernel. When we multiply it by an element of the kernel, since the kernel is closed, this can't give an element of the kernel, because if it gives an element K2 of the kernel, then we can write G1 equals K2, K1 to the minus 1, so this belongs by closure to the kernel, but we are assuming this does not belong to the kernel. Now given that G1 goes in H1, if we multiply it by an element of the kernel, where does it go? If we apply the function f, we have f of G times f of K, and since K is in the kernel, f of K is E, so it is simply f of G1, which is H1 because it goes in H. So it still goes in H. It still goes in H1. So if an element G goes to H, if we multiply it by the kernel, it will still go in H. So all the elements G1 K, G1K1, G1K2, G1K3 and so on, for all the elements in the kernel go in H1. We write the set like this, G1K, and this is called a left coset of the kernel. And of course, so these are different elements of G1, which is the set of elements sent to H1. these are all sent to H1, so all these elements are elements of G1. And since there is this correspondence, its size is exactly the size of the canal. So we have seen that G1K is a subset of G1. But is it the whole G1? Maybe there is an element in G1 which is not in G1K. And with the same argument we can generate G1'K, which is also a subset of G1. So the question is, are these the same set? So if you start from the canal and you multiply each element by G1, do you generate all the set G1 which sends its element to the element on which G1 is sent? Well, we simply see that if G1'K is not generated by G1K' for elements of the canal K and K', by applying the homomorphism, we would have f of G1' different from f of G1, but they are both sent to H, so H1 different from H1 because they're both sent to H1. So clearly all the elements here must correspond to one element here, so these are the same set. So we can write G1 as G1K for any element G1 in G1. So by writing Gi equals Dik for an element Gi in Gi, we can now write this like this, where we substituted Gi with Gik. So G1 is G1K, G2 is G2K, and all these sets have the same dimension of the canal, so they all have the same dimension. Because we have seen before there is a correspondence with the elements of the canal. And of course, don't confuse these with the subgroups. These are not subgroups. These are subsets of G. But the only subgroup here is K. It's the only one which is closed and contains the identity and the inverses. So they are not subgroups. So don't confuse the cosets with the subgroups. They are very different things. Only the canal is a subgroup. Notice that we have done all the arguments for the left cosets, but we could have done the same for the right cosets, and the result would have been the same. So we must have this correspondence. The right cosets of the canal are equal to the left cosets of the canal. And this is not a property of all groups. If A is a group, this is not necessarily true. G1. This is a property of the canals. The subgroups G with the canal property are called normal subgroups. And this property can be written as to some element G1K here must correspond one element K' G1 here. And we can write this as K equals to G1 to the minus 1 K' G1. And this must hold for any element K in the canal. So for any element K in the canal, there must be another element in the canal K' for which this relation holds. These two elements K' and K are said to be conjugated, and they are conjugated by the element G1. And by considering all the cosets Gi, K, we have that in normal subgroups K, for any element K', if you conjugate it with one element G, so you do G, K', G to the minus 1, you still obtain an element in the canal, so you don't go out the subgroup. So if you have a set G of actions and a subset K of actions, if the subset K of actions is a normal subgroup of G, then you can do an action G, which may also affect the subset K of actions. So you end up with this, and this is G. Then you do an action only in K, and this action will not affect the rest of the actions of G. This is basically the intuition behind the normal subgroup. So this remains like this, and you do this, and you have done now KG. Then you undo G, and by undoing G you still affect K, but G is completely undone because K did not affect the rest of action, so you can still undo G with G. So doing G to the -1 Kg gives here nothing, exactly like here there was nothing, and you end up with an element K prime. So it is as if you had done only an action inside K. And this must be because of the preservation of structure, because if you're doing operations in the kernel, in the set G, it's like doing operations in H in the identity, but operations in the identity do nothing. So if you do operations in the kernel, you can't affect the outside structure. Otherwise, also here the outside structure would be affected by operations which do nothing, but operations which do nothing don't do anything, because when you do the homomorphism you send all this to E, so you lose information of the operations you have done in K. If by doing operations in K you had affected the outside structure, then you wouldn't necessarily lose information of the outside structure. So we now have a bijection between the set of cosets of the kernel and the image of the homomorphism. So we started with a homomorphism and we ended up with an isomorphism. So when you have a homomorphism, you can always find an isomorphism. Of course, since they all have the size of the kernel, we have that the size of the kernel times the number, so the size of the set of cosets is equal to the order of the group G, or also the order of the group G divided by the number, divided by the order of the kernel is equal to the order of the set of cosets. In fact, the set of cosets is usually notated as G divided by K, G division K. This can be seen as a quotient group between G and the kernel, and we have that it is isomorphic to the image, and this is the isomorphism theorem. Notice that for a homomorphism to be already an isomorphism, you need to have already a one-to-one correspondence, so you need the kernel to be just the identity element. If the kernel is the identity element, you have the same number of elements in the set G and the same number in the set H, so your homomorphism is automatically an isomorphism. So we can say that a homomorphism is an isomorphism if and only if the kernel counts only the identity element. Now we quickly answer some doubts you may have. Homomorphisms of homomorphisms are always homomorphisms, obviously, because if you maintain the operation structure and then you maintain again the operation structure, the result is always maintaining the operation structure. And of course also f of a to the -1 is f to the -1 of a. You can verify it easily from here. Now we go back to direct product of groups. We have seen the direct product of two cyclic groups, and we had that Cn is a subgroup of C and M. Cn is a subgroup of C and M, and you can write Cnm as the product between Cn and Cm if and only if the greatest common factor between n and m is 1. Now we want, in general, given two subgroups of our general group I, find sufficient conditions for which we can write I as a product of these two groups. Above we have a necessary and sufficient condition. Unfortunately, we will not find a theorem today for which we have necessary conditions, but we will study the direct product theorem, which gives us at least sufficient conditions. We are doing it after having studied a bit of homomorphism because it will be useful. In particular, the result which will be useful, and you have to remember that a homomorphism is bijective if and only if the kernel is E. Remember this condition for a homomorphism to be an isomorphism, because it will turn out useful in a very few minutes. In fact, we can try, for example, to find a homomorphism which sends the element G8 to the element G times H in I. Since this is a homomorphism, we must preserve the multiplication structure. So we know that this is G1, G2, H1, A2, and this is sent by our definition to G1, G2, H1, H2. And this must be equal to this because of the preservation of the multiplication structure. So at the two extremities we have the same elements, but in the center they are inverted. So we must have H1 G2 equals G1 A2, and this must hold for any H and for any G, for any H of H and for any G in G. So taking any two elements, one from H and one from G, they must commute. So to have a homomorphism with this property, we must take two subgroups in which the elements commute between them, although the two subgroups need not to be abelian, but only a combination of two elements, one from one group and one from another group, need to commute. So we already found a homomorphism. For it to be an isomorphism, it must be bijective. So for it to be surjective, it is sufficient that any element in I can be written as a combination of an element of G and an element of H. Instead, for the inactivity, it is sufficient that the kernel is made only of the identity element. So let me write the conditions here. This is the condition for surjectivity. Every element in I must be generated by the elements in G and H. And this is a condition for homomorphism, because if we have this condition, we can easily find a homomorphism as we did. And then this is the condition of inactivity. Now we can write it in another way, which is more easy to verify directly. Now we would have to directly check the homomorphism, obviously, to verify this. But we can give a condition, a sufficient condition, to have this. We can write it like this. So if we take an element from the kernel, we must have G equals H equals E, so that element must be the identity, and we can write it like this because of the homomorphism we created. So G equals H to the minus 1. So since H is the inverse of G, H is in G, because the inverse of G must be in G, and also G is the inverse of H, so G is in H. So these two elements from the kernel belong to the intersection between G and H. So for the kernel to be only the identity element which is sufficient, not necessary but sufficient, that the intersection between G and H is the identity element, because only elements in the intersection can be in the kernel. But if the intersection is made only by the identity element, then the kernel must be made only by the identity element. So we can write our sufficient condition like this. The intersection between G and H is only the identity element. So this is a direct product theorem which gives sufficient conditions for which you can describe I as a direct product of two subgroups G and H. So this was a very quick introduction to group theory. See you next time.